In previous video, we have seen that Fourier integral of a random process does not necessarily converge and quite often does not converge. And we cannot use the Fourier transform directly, straightforwardly to analyze LTI systems, deterministic LTI system, when they are interacting with random processes. So in this video, we want to analyze LTI system, deterministic LTI system, when they are interacting with wide sensor station random processes. So in this case, because Fourier transform of the random process does not exist, we apply the Fourier transform on the statistics of the inputs and outputs. So we have seen that we cannot apply Fourier transform to a wide sensor station random process. Fourier transform of x of t does not exist. Fourier transform of the output y of t does not exist as well. So we apply it on the mean. The mean analysis, because it's only one single component, like if it is wide sensor stationary, mean of x of t is constant. And if you have LTI systems, the response of the mean of the output, so mu x, which is constant, times h of 0, which is the DC gain of your filter, is equal to mu y. So the DC analysis of your LTI system is very easy. However, if we assume that your random process is wide sensor stationary, the autocorrelation function of that Rxx of T1 and T2 is only a function of Rxx of time difference, which we say T2 minus T1, and we say that we abbreviate and we don't write these to 0 and this and that. So in that case, a random process, wide sensor stationary random process, is characterized by its autocorrelation function plus its DC, which is mean of x of t. Now we could apply, because this is only one time index, which is 2, which is equal to t2 minus t1, which is the time difference. So I could apply Fourier domain, Fourier transformation. I could transform that, and I define power spectral density. So this is defined as integral of Rx x of 2 e to the power j omega 2 minus here, and then d2 from minus infinity to plus infinity. So this Fourier transform of autocorrelation function, we call it power spectral density. Why? It is power, y is the density, y is the spectrum. So these three words, where are they coming? We will give some more insight, and we will prove some theorems and so on. And then these components of this name, these three components, they will have more meaning very soon. So this is the definition. This is basically the dot product of Rx of 2 e to the power j omega 2. Remember that when you put a dot product, you put a conjugate on the second signal. And the Fourier inverse of that is defined as. So it's kind of one-to-one relationship, and we show it by a Fourier transformation, because having this information is equivalent to that, and so on. So we can transform between these two domains in a one-to-one manner. So obviously, for this signal, if you replace these either in this equation or that equation, if you replace t by 2 minus 2 and then apply conjugate, you can easily prove this one. This is exercise for you. So because of this property, this function is equal to it has some kind of symmetry in it. So we have proven this one, because you know that Rxx of T1 and T2 is equal to mean of x of T1 x of t2 conjugate, okay, and rx x of t2 and t1, okay, is equal to mean of x of t2 and x of t1 conjugate. Now if you apply a conjugate on the second one, these will become equal to this one. So and then if this is white sense stationary, this is equal to rx x of 2, and this is equal to rx x of minus 2. So for white sense stationary random process, either complex or real, we always have this one. So because of this symmetrical property, in time domain, this function should be real. So Sx x of omega is always real and is always positive. So it's a non-negative real function. So you can prove this as an exercise. So this is your first exercise, and this is the second, and this is the third exercise. Prove all of them, and then you will. Because it's real and non-negative, you could call it power. So we'll have more in-depth understanding about these once we prove a theorem. So if this function, autocorrelation function, or the random process, if one of them are real, of course, if this guy is real, this one should be real, but there are cases that this one is real, but not the first one. So if this signal is real, you could you can write this one as a one-sided integral. Okay, so we could have a 2 here because the imaginary part is 0 because of this. So this is another exercise, and obviously because this is always true, and then the negative part and the positive parts are equal, so then when you add them together, e to the power of minus j omega t plus e to the power of plus j omega t, or sorry, 2 is equal to twice cosine of omega 2. So you could have a one-sided integral but twice, but instead of e to the cosine. This is another exercise.